Maybe Muraz is not present, right? Today?
Yes, actually, sir, electricity issue.
Okay. So here it depends on the material that you are using. For this material, that is for this material, your ratio becomes 3:1. If you change the material, your ratio can be different as well. It can be 2:1, it can be 2.5:1, but normally it is 2 to 3 times. So here, for this material, if we do not change this material, it will remain as three times. So this is the okay. Now we are going to see the transient because the main purpose of DC was to find the middle point and W and W. Got my point? The main purpose of DC analysis was to find what is the perfect WW ratio, and we got our perfect WW ratio, that is 3:1. We already got it. Since we already got it, now we are no longer required. We no longer require the DC analysis anymore. We will now see the transient. So transient, this one will be what? Be in CL, this two. That is the voltage. As you can see here, let me. So the green one is your input, the red one is your output. So when your input is 1, your output is 0. When your input is 0, your output is 1. As you can see, it has some rise time and it has some fall time because that is not the input, the output. Output has some rise time and fall time. This is because of the capacitor, because you are using capacitor as your output device, right? So it needs some time to charge and it needs some time to discharge. Okay, remember. So this is your output versus input graph. This is the transient graph that you are looking for. You can make it bigger. You can make it if you click the graph, and if you right click, you will get a information and properties. If I click the properties, you can change the shape of the graph. You can make it like this, your wish, no problem. For the visibility purpose. Now we want to simulate. We will try to simulate these spice source file, okay, or write a source file for this circuit. Here, this is a low pass filter. Only 3 elements are here. 3 elements. One element is your input. One element is your resistor. One element is your capacitor. And this source is 1 volt source, and it has 1 megahertz frequency pulse. So this is the pulse. So we will try to simulate the graph. At first, we have to write a code. Okay, we have to write a code. Now, at first, before writing a code, let's make some noding. This is a 0 node. That means this node and this node, this is 0, right? Let's say this is your 1 node, and this is your 2 node. Got my point? 0, 1, 2. Now here, what are the elements you have to keep here? Very simple. Go to this one. Fine. Here, this model specification we do not need, because this is not a PMOS, this is not an NMOS. So we do not need. DC analysis we do not need, because we are not going to do the DC analysis. We are doing the transient analysis only. Got my point? Got my point?
Yes, sir.
So the other things we do not need. I'm going to close it. Here, we do not need any MOSFET, because we do not have any MOSFET. So I'm going to keeping the MOSFET out from here. We do not need any VDD, because we do not have any VDD. So we only have a V in. Here we only have a V in, that is 1 volt. So let's write. It is connected between 1 to 0, and it is pulse. It should be 1 volt. and this timing it will be changed. This timing it will be changed. Why it will be changed? Because we have a 1 volt 1 megahertz. Remember, this is 1 megahertz. So what is 1 megahertz? What do you mean by 1 megahertz? Your frequency is 1 megahertz, right?
Yes, sir.
What about your time period? That means the period. T is equal to 1 by f, right?
Yes, sir.
So what is the f? Can anyone calculate?
1 into 10 to the power minus 6.
Minus 6. 1 into 10 to the power minus 6. So what will be the value?
0.5051.
1 megahertz means maybe 1 microsecond, right?
Yes, sir.
1 microsecond is your, that means if you do the opposite or inversion, you will get 1 microsecond. That is your total period, total time. If it is 1 microsecond, so how much will be this one? Let's say 0.5 microsecond.
0.5 microsecond.
Okay. So let's go there and write. This will be 0.3 nanosecond, 0.3 nanosecond, 0.3 nanosecond. This will be 0.5 microsecond, right? 0.5 microsecond, not ns. And this will be 1 microsecond, right? And you can not 0.3, you can write 1 nanosecond because microsecond is bigger than nanosecond, right? 0.3 is not needed. We can do that, right? Because this is the delay time, this is the rise time, this is the fall time. Because previously it was 20 nanoseconds, compared to 20 nanosecond, 0.3 nanosecond was small, but compared to 0.5 microsecond, 1 nanosecond is even smaller. So we can give it. Or if you want to keep it as 0.3, you can keep it, no problem. Now here, the transient analysis, how much we want to see? At least we want to see 4 nanosecond, right? 4 microsecond. That is 4 cycle. You want to see how much? Four cycle. I want to see 4. Okay, no. Let me go and check the question again. And produce, show, and below produce a transient analysis circuit over a time. Okay, it is given. It is given. So it is not asked. Over a time period, over a period of microsecond, with an increment of 10 nanosecond. So we can only check for 1 microsecond. A period of microsecond, right? A period of microsecond means 1 microsecond. Got my point? That means only 1 cycle. Only 1 second we can what? Only 1 second we can check. We can see. Got my point? That means we have to do the transient analysis over a period of microsecond. That means only 1 microsecond. An increment of 10 nanosecond. Okay, fine. It is given already, so we cannot do anything else. So it will be 1 microsecond and it will be 10 nanosecond. And the circuit, remember, from there is a resistance that is between 1 to 2, and that is 50 ohm. So I'm going to write, there is a R. Let's write RL or RS because it is in series. It is in between 1 to 2, and the value is 50 ohm. Since it is ohm, that's why, okay, let me make it a bit bigger. Since it is ohm, that's why I'm not going to write anything else with this one. Okay. Then we have a capacitor that is in between. Here it was 2, here it was 0. So in between 2 to 0, we have a capacitor that is 1 nanofarad. So I'm going to write it here. In between 2 to 0, not 3 to 0. It is how much? 1 nanofarad. 1 nanofarad means this will be 1. I will write 1 nanofarad, only 1 N. That's it. Yeah.
transient sir is 1 nanosecond or 1
What?
transient sir.
I didn't listen to your word. What?
The transient sir.
Transient, yes.
It's 1 nanosecond or
It is 1 microsecond, not nanosecond. Sorry, 1 microsecond. Okay. Okay, let's try.
Yes,
Let's
sir.
try. Let's try and see. Okay, at first save it for later use. LPF, low pass filter. Now I want to make it a circuit file. Save as .cir. Let's see. Okay. I'm not sure whether it will be okay or not. Let's see. Let's check. No, there is no error. Let's see. What we want to see? We want to see the voltage of V in and voltage of CL. Okay. Can you see that?
Yes, sir.
This is the output that you want. As you can see, your input was the pulse, that means this pulse, and your output is also this pulse. So the circuit is passing your input, right? Your input is passing. That means it is a low pass filter. Still, it is passing. Now, what I can do, I can increase the frequency. Okay. Let's do one thing. Let's check for 3 microseconds. So 3 cycle will be there. As you can see, your input is passing. You have an input, you have an output. Got my point? Although the output is not exactly square wave, but it is close to square wave. Your output, that means the red one. Red one is not exactly square wave, but is square wave, almost. Okay? So your input is passing. That means it is a low pass filter. It is already it is passing your input. But what if I change? What if I change the frequency? What if I increase the frequency? What if I make it 0.1 microsecond and 0.2 microsecond? Got my point? What if I make the frequency 5 megahertz? 5 megahertz. 5 megahertz means 0.2 microsecond. Okay. What if I increase the frequency? This is the circuit of low pass filter. This is a circuit of what? Low pass filter. What do you mean by low pass filter? If I increase the frequency, what will happen to the output? What will happen to the output?
Decrease.
Output will be smaller because it is not passing your input fully, right? Did you understand what I have said? Low pass filter means if I increase the frequency, your output will be what? Your output will be what? Smaller.
Decrease.
Decrease. Okay. So let's check. Let's try. It is 1 megahertz. Now I want to check 5 megahertz. This is 5 megahertz, 0.1 and 0.2 microsecond. So if I do that, you will see. Okay, wait. Now this is no longer 1. Let's make it let's make it 1. As you can see, your input is square wave but your output is not a square wave. Can you see that? Your output distorts. Okay. Your output is distorted. Can you see that?
Yes, sir.
That means your that means your input is not passing 100%. It is passing a small amount. Okay, let's increase the frequency even more. Let's increase the frequency even more. How? Let's make it 10 megahertz. So it is 0.1. It will be 0.05. and this one will be, okay, let's make it 1, so maybe 0.5 microsecond. Now it is 10 megahertz. See, your output has become even smaller. Previously, it was a bit bigger. Bigger means, right? It's a bit bigger. Now it is even smaller. Got it? So the more frequency you are going to increase, your output will be very smaller. So now let's try a bigger one. Let's make it 100 megahertz. For 100 megahertz, what will be your time? For 100 megahertz, what will be your time? Can anyone calculate this for me?
So 1 nano হয়ে যাবে স্যার
1 divided by 100. Okay. It is 0.01 micro, right? So if I make it 1000, yeah, 10 nano. It will be what?
10 nano
10 nano. So it will be 10 nano. So it will be 5 nano. And let's make it 0.1 because 10 nano and 1 nano is close. Okay, 0.1, 0.1. And this is how much we want to see. Let's say we want to see 30 or 50 nanosecond. We want to see 50 nanosecond with an increment of 0.1 nanosecond. Okay, let's try. Can you see the difference?
yes sir
What happened to your output?
Very small, sir.
Your output become what?
So much decrease, sir.
Yeah, your output decreases because it is a low pass filter. So more frequency you are going to increase, your output will be so less. So this is one way why I am showing you this. This is not related to your VLSI. This circuit is not related to your VLSI, but still why I am showing you this. Can anyone give me an idea? Hello?
yes sir
Any idea?
sir
Okay. So I am showing you this to show you that means you can simulate any circuit. You can simulate any circuit by using coding. Understood? So you have seen Proteus, right?
yes
You
sir
have seen Proteus. In Proteus, what you do? You bring out your resistor, capacitor sources, right? Your oscilloscope. You make the circuit, that is, you draw the circuit and you simulate the circuit. But here, you have used a different method. What is that method?
coding
You use coding to simulate a circuit, right? So there are options. There are many cases that you will see. You will see that you have to simulate your circuit by using coding. So this is another way. So don't be surprised in future if you see you have to make a circuit or you have to simulate a circuit by using a coding. Okay, it is possible. Okay,
Yes.
so your lab number 1 is finished. So we have done these as you have seen. So this is possible to simulate your circuit using coding, and I hope you will do that. Okay. Be very careful about dengue fever. Okay, because nowadays the dengue is very prominent. Okay, now yours lab number 2. That means the experiment number 2. The circuit simulation using SPICE. What is that? CMOS NAND and CMOS NOR. Okay. So this will be our second lab. So in this lab, our objective will be to identify and mark different nodes of NAND gate and NOR gate to create the circuit file for NAND and NOR gates, to analyze the circuit using SPICE transient analysis capability. So I'm going to do NAND gate for you. You will do NOR gate for me. Okay, everyone?
Okay, sir.
Okay. So this is the NAND gate. As all of you know this, right? Do not see this. Do not what is that? Worry about this. We have done our theory about transistor sizing. Abdullah, আমরা কি আমাদের transistor sizing নিয়ে পড়াশোনা করছি?
Yes, sir.
Okay. So all of you submitted your assignment and lab report, and all of you participated in midterm exam. Is there anyone who missed?
Sir, lab report বাকি আছে আমারটা।
আচ্ছা, কেউ কি তোমরা midterm miss করছো? Did anyone miss the mid exam or mid viva? Okay, I will give you a list. Okay, I will give you a list in the next class, or maybe in the next class, and showing you who means the mid or who means the something, and I will give you a mark after one. মানে 1 আগস্টের পরে আমি তোমাদেরকে একটা মার্কিং দিব সবাইকে about the midterm and viva. Okay.
Okay, sir.
Okay, now here this is your NAND gate. In this NAND gate, you can see you have two inputs. We have two input and NAND gate. One is A. This A is connected to the PMOS as well. One is B. This B is connected to the PMOS as well. Now, what is the first thing you have to do? You have to draw the circuit, right? Then what you have to do? You have to make the name, right? You have to make the name. What will be the name? Anyone? Okay, let's write. This is MPA. This is MPB, because MOSFET PA, right? It's connected to the A, that's why. MOSFET PB, that's why that is the name I'm giving. You can change the, you can use different name as well, no problem. This is MNA, MOSFET NA, MOSFET NB. Okay, now after the name, oh, by the way, there is a capacitor here as well, because the LED will not work in your simulation. Let's write it CL. Right? This thing is called VA. This is called VB, because there should be a V in front of any voltages, right? Now, after the naming, what do you have to do? You have to sizing, right? You have to do the sizing. What will be the sizing of this one? Have we finished the transistor sizing in theory?
Yes, sir.
Okay, so the sizing will be, as you can see, if we use 3:1, because for these lab number 1, 2, 3, the material we are using in our first lab, we have seen our ratio is 3:1, right? 3:1. So if we use 3:1, our sizing will be, since they are in series, it will be 2, because it is NMOS. So this one will be double, because there is two MOSFET in series. So this one will be double. So double means 2. Here 2. This one become double. Okay. Now here we have only 2 paths. One is this one. Another one is this one. In these 2 paths, we have only one MOSFET, right? Only one MOSFET in this path, only one MOSFET in this path. So these 3 will be one time, 3 into 1. That means 3. These 3 will be multiplied by 1 as well here for 3. So this is your sizing. So 3:1 become 3:3:2:2. This is your sizing. That means if 1 is equal to 4 micrometer, what about your 2? 2 become 8 micrometer. What about your 3? How much is 3? Anyone? Anyone?
1 4, sir.
See, 1 is equal to 4, 2 is equal to 8, 3 is equal to 12.
8. Yeah.
12 micrometer. Okay, remember this. It is 12 micrometer. Okay, so your sizing is done, your naming is done, your drawing is done. Now the only thing you have to do, that is your what? No, not only thing. Next thing you have to do, that is your noding. You have to name the node, right? Node. So this is your, okay, let's use a different color. This is your node number 0. So this ground is also your node number 0. Next is your node number 1, that is your input A. That means this part, the whole part is 1. This is your 1, node number 1. Now next is your node number 2. Which one will be node number 2? Your B. This is your node number 2. Now this next will be node number 3. Which one will be node number 3? Let's write this is your node number 3. That means this and this. Next come your node number 4. Which one will be node number 4? Let's start. This is your node number 4. What do I mean by this? This means from here to here to here to here. Okay. Next come node number 5. What is node number 5? Here is node number 5. That means this part. Is there anything that I missed?
No, sir.
Okay. So after that, so from here we will do our what? We will do our coding. Let's take a screenshot. And write our code. This is the screenshot that I am taking. Let's write our code, not this one. We will copy the code from the CMOS NOT, same code, just modify. Now we are going to use a text document. Let's say NAND. Okay. CMOS NAND. Here, how many MOSFET do we have in this circuit? How many MOSFET do you have?
4.
4 MOSFET, right? So one is MPB, MPA, MPB, MNA, MNB, right? So 2 MOSFET, 2 P MOSFET, and 2 N MOSFET, right? So that's why I have copied 2 MOSFET, 2 P MOSFET, 2 N MOSFET. So this one is MPA, this one is MPB. This is MNA, this is MNB. Understood, everyone?
Yes, sir.
What is your NPA?
Yes, sir.
Where they are connected? Where they are connected? NPA.
3 and 4.
So drain, gate, source, body, right? Drain, gate, source, body. Where is the drain of this one?
3.
No,
Four,
drain,
four.
drain is connected to the 4, right?
Yes,
At the
sir.
bottom. So 4, 3, this one, 4, 3, 1, 1, right? No,
Yes.
4, 3, no, now drain, gate, source, body, sorry. Drain, gate, source, body. What is the drain? Drain is 4. What is the gate? Gate is 1. What is the source? Source is 3. What is the body? Body should be also 3 because body and source, they are connected. So 4, 1, 3, 3. Understood?
Yes, sir.
So let's write it here. 4, 1, 3, 3. It is PMOS. And what is the width? What is the width? 3. That means
3.
12, right?
Yes, sir.
Okay. And L will be 3. Next one, try the next one, MPB. What is the drain? Drain is 4.
4,
What is the gate?
2,
2. What is the source?
3, 3.
3, 3. So 4, 2, 3, 3. That's right. 4, 2, 3, 3. It is also P type, and W is equal to 12 because it is the sizing is 3. That's why. Now come to the next one. That means the NMOS. What is the connection of M and A? What is the drain? Drain is 4. What is the gate? Gate is 1. What is the source? 5.
5.
Body is
5.
also 5. And what is the sizing?
8.
2. That means 8, right?
Yes.
So 4, 4, 1, 5, 5. The sizing will be 8. Next one, 5222. 5200. Sorry. 5200. Understood? Why? Because drain is 5, gate is 2, source is 0, body is also 0. And the sizing will be 8. Now, your VDD, where the VDD is connected?